Have you ever just, stopped and wondered what the actual rule book for the universe looks like? I mean, for everything from the tiniest particle to the biggest galaxy. Well, that's what we're going to do today. We're going on a little quest to unlock the fundamental principles that govern all of reality. So, yeah, let's dive right in. So, here's our game plan. First, we're going to look at how we even start asking these huge questions. Then we'll zoom in on physics itself. After that, we'll get to the really good stuff, the four forces that basically run the entire show. Then we'll cover the unbreakable laws they all have to follow. And finally, we'll tie it all together and see why any of this really matters to you and me. All right, first things first. If you want to write a guide to the universe, where do you even begin? How do you make sure you're getting it right? It all comes down to this one simple question. But man, is it a big one. This question has been bugging humanity for, well, forever. And to answer it, we had to invent a pretty powerful tool. And that tool is science. The key thing to remember about science is that it's not really about random flashes of genius or eureka moments. It's a process. It's all about being systematic, organized, and really rigorous. It means you carefully test your ideas, you watch what happens, and you think clearly about what it all means. But, of course, a tool is only as good as the person using it. So the quest for knowledge also needs the right mindset, what we call a scientific attitude. And that just means being flexible, being open-minded, being willing to admit you're wrong. It's all about following the evidence wherever it leads, not just trying to prove what you already believe. And this right here, this is the playbook for how it all gets done, the scientific method. It's a step-by-step loop, really. You see something, you come up with a guess, a hypothesis about why it happens. Then you test that guess over and over. And if it holds up, you can start using it to predict what's going to happen next. That's how we build knowledge we can actually rely on. Okay, so now that we have our method for asking questions, let's start to narrow our focus. If science is like this giant library of knowledge, we're heading to one very specific, very fundamental section: physics. The word physics actually comes from an old Greek word that just means nature. And that's really what it is. It's the study of nature's most basic, most fundamental rules. We're talking about the absolute essentials: space, time, matter, energy. It's the bedrock that all the other sciences are built on top of. And the scope of physics, it's just huge. Think about it. It covers everything from the simple mechanics of throwing a ball to the nature of light itself, to the weird and wonderful world of quantum mechanics that dictates how atoms work, all the way up to relativity, which is literally the study of reality at the speed of light. It's a lot. Okay, but here's where it gets really, really cool. For all that complexity we just talked about, it turns out that every single thing that happens in the entire universe, every push, every pull, every single interaction, it's all governed by just four fundamental forces. That's it, just four. Isn't that wild? Think about it. Everything from a star exploding millions of light years away to a thought firing in your own brain, it all just boils down to these four forces playing with each other. First up, the old classic, the one we all know and love: gravity. It's the force of attraction between any two things that have mass. Simple, right? It's what's keeping you in your chair right now, and it's what keeps planets swinging around the sun. Now, it's actually the weakest of the four by a long shot, but its reach is infinite. Next is the electromagnetic force. Now, this one is responsible for, pretty much your entire day-to-day life. It's the reason your hand doesn't just pass straight through your desk. It's electricity, it's magnetism, it's light itself. It's the force that holds atoms together to make molecules, to make you. But wait a second, what holds the center of the atom together? You've got all these protons packed in there. They're all positively charged. They should be repelling each other like crazy and flying apart, right? Well, that's where the strong nuclear force comes in. It is incredibly powerful, but it only works over teeny tiny subatomic distances. It's basically the superglue holding the core of every single atom in the universe together. And finally, we have the weird one, the weak nuclear force. This one's a little more mysterious. It operates deep inside elementary particles, and it's the force behind things like radioactive decay, like when a neutron inside a nucleus decides to turn into a proton. It's a crucial part of the process that makes stars shine. And this table, wow, this really puts the power gap between these forces into perspective. So if we say gravity has a strength of just 1, the weak force is 10 to the 25th power stronger. That's a 1 with 25 zeros after it. The electromagnetic force is way, way stronger than that. And then the strong force is almost 100 times stronger than that. The difference in scale is just, it's mind-bending. So we've got these four forces, these powerhouses of the universe. But it turns out even they have a boss. They all have to play by an even higher set of non-negotiable rules. These are nature's unbreakable laws, the great conservation laws. Now, there is one condition. These laws apply perfectly to what scientists call an isolated system. You can basically think of it as a closed box with nothing getting in or out. And what's the most perfect, most ideal isolated system we know of? The entire universe itself. Now, just look at this table. This is where things get really beautiful. Each law exists because of a deep, profound truth about the universe. The law of conservation of energy. That energy can't be created or destroyed, that exists because the rules of physics are the same today as they were yesterday and will be tomorrow. Then there's linear momentum. That's conserved because the universe's rules are the same here as they are a billion light years away. And angular momentum, why a spinning skater speeds up when they pull their arms in, that's conserved because there's no special up, down, left, right direction in space. Every unbreakable law comes from a perfect symmetry in the fabric of reality. It's incredible. And we've got to add one more to our list of unbreakable rules, the law of conservation of charge. Super simple. Inside that closed box, the total amount of positive and negative charge will always add up to the same number. Okay, so forces, laws, symmetries. This all might feel a little abstract, so let's bring it back down to earth. What does any of this mean for us, for society? Why does this big quest for knowledge even matter? I think this quote just sums it up perfectly. Figuring out these fundamental rules isn't just for textbooks. When we understand something like electromagnetism, we get game-changing technology like computers and the internet. And sometimes it works the other way. We build new tech, like giant particle accelerators, and that lets us discover totally new physics. It's this amazing feedback loop that has a direct impact on all of our lives. And that brings us to the end. Right now, one of the biggest, most exciting quests in all of physics is something called unification. It's the search for a single, beautiful, elegant theory that can describe all four of these forces as just different flavors of one single master force. And so I'll leave you with this question to chew on. What happens when we find it? What new technologies, what new understanding of reality will we unlock when we finally figure out that ultimate rule in the cosmic code?